Hello, my name is Michael O'Reilly, and this is my lab report that covers Lab 4, which is magnetic braking with Faraday. The two main problems and purpose of this lab is to find the effect that an induced current has on a falling magnet through velocity and comparing the results to the computing model, which we will discuss later. As for the fundamental principles that are used in this lab, we'll use Faraday's law, Lenz's law, and the magnetic field of a bar magnet. And the most important results that we will find in this lab are that the magnet falls more slowly through the foil tube than outside of the tube, and the coding results are more accurate than the measured results. So the procedural setup is shown to the right with the foil tube and dropping the bar magnet with the north pole facing down into the tube. Some assumptions that we made in this lab were that the bar magnet did not hit the sides of the tube on its path in, and air friction was insignificant. As for the data, we measured the time for the magnet to fall through the foil tube 5 different times, with the results for each trial shown here below. And the time needed outside of the tube to fall the same distance from rest was around 1.94 seconds. The magnet fell more slowly inside of the tube due to induced current and the electric field that is inside the foil. The resulting magnetic field from the foil opposes the magnet's motion, as discussed by Lenz's law. Okay, so now on to the coding complement for this lab. Our code that we created for this lab did 3 main things for us. First, it created a diagram of the bar magnet and the foil. It also displayed a graph of the velocity of the magnet versus the time. And finally, it produced the time needed to fall through the foil tube, which is shown by the computing model, which is around 1.20 seconds, which is about only 0.01 seconds faster than our measured results, so it's pretty close. The code accomplishes this by having 2 main functions, dipole B, which gives us the magnetic field from the magnet, and the other function, which gives us the change in flux with respect to time. These were used in a while loop while the magnet was inside the tube, as you can see in the top coding part. The bottom part of the code shows the magnetic force on the magnet due to the induced current in the foil. Now on to the interpretation of the code. So in order to make the code more accurate, more rings could be included to represent the model as a tube, more than just a collection of rings. When the magnet is flipped and dropped with the south pole facing down, the time is still smaller than it would be normally. Deflux dt is still up, so induced current and the magnetic force on the magnet is in the same direction as before. The red color on the tube represents the counterclockwise current, and the blue color represents clockwise current, which is determined by Faraday's law. And the velocity v-time graph shows no net force inside of the tube. Fmag is equal but opposite to the force due to gravity, as V is constant. Okay, so finally to the analysis of this lab. If the resistivity of the conductor was reduced essentially close to 0, like a superconductor, the current would increase significantly and the magnet would fall through the tube, slowing down and hovering in the middle of the tube. If holes were cut in the tube, the current might be interrupted and not flow in the tube with as great of a magnitude as previously, and some of the rings in the middle would not be complete and thus not have a current in it. Thank you very much for listening and watching my presentation. Take care.